Every mass extinction explained. Species disappear naturally, but a mass extinction removes an unusually large share of life in a geologically short interval. Scientists often use roughly 75% of species lost as the benchmark for a major mass extinction. We reconstruct these crises from fossils, rock chemistry, ash layers, and abrupt changes in ancient ecosystems. Earth has experienced 5 famous mass extinctions, while today's biodiversity crisis may be creating a 6th. Mass extinction number 1. Late Ordovician. Around 444 million years ago, most complex life lived in shallow seas filled with trilobites, brachiopods, and reef communities. The Late Ordovician Extinction is commonly divided into 2 major pulses linked to rapid environmental change. Large ice sheets expanded across the southern supercontinent Gondwana, cooling the planet and locking water on land. As glaciers grew, sea level fell, and vast shallow habitats disappeared from continental shelves. When the ice retreated, rapid warming and expanding oxygen-poor water created a second wave of stress. Roughly 85% of marine species disappeared, making this one of the largest crises in the fossil record. Surviving lineages diversified again during the Silurian, but the recovering oceans were not identical to those before the crisis. Mass extinction number 2. Late Devonian. The Late Devonian crisis unfolded through several extinction pulses between roughly 372 and 359 million years ago. Before the crisis, armored fishes, early sharks, and enormous reef systems dominated many tropical seas. Deep-rooted plants spread across land, transforming soils, weathering rocks, and moving more nutrients toward the ocean. Extra nutrients may have fueled algal growth and decomposition that removed oxygen from broad marine regions. Large-scale volcanism, climate shifts, and changing sea level may also have contributed, and no single cause explains every pulse. Across the prolonged crisis, roughly 3/4 of species disappeared, with tropical marine ecosystems hit especially hard. Complex reef building remained limited for millions of years, while new vertebrate groups expanded in the changed world. Mass extinction number 3. End-Permian. About 252 million years ago, the End-Permian extinction became the most severe known biological crisis of the past 500 million years. The Siberian traps released repeated pulses of lava and gases across an immense region. Carbon dioxide and other volcanic gases drove rapid global warming and destabilized the carbon cycle. Warmer water held less oxygen, circulation weakened, and oxygen-poor or sulfidic zones spread through the seas. Some tropical regions became lethally hot, while acidification and ecosystem collapse removed additional refuges. Estimates vary, but roughly 80 to 90% of marine species vanished, along with major losses on land. For millions of years, extreme heat and low oxygen oceans delayed the return of complex, stable ecosystems. Mass extinction number 4. End-Triassic. About 201 million years ago, the supercontinent Pangaea started rifting apart, where the Atlantic Ocean would eventually form. Enormous volcanic eruptions spread across the rift in the Central Atlantic Magmatic Province, or CAMP. Geological evidence indicates repeated bursts of volcanic carbon dioxide during the extinction interval. Rapid warming, ocean acidification, and changes in oxygen availability placed ecosystems under intense stress. Many conodonts, large amphibians, reef builders, and crocodile-line competitors vanished during the crisis. Estimates commonly place the loss at roughly 70 to 80% of species. Several dinosaur lineages survived and diversified into ecological roles left open after the extinction. Mass extinction number 5. Cretaceous-Paleogene. 66 million years ago, an asteroid roughly 10 kilometers wide struck near today's Yucatan Peninsula. The impact excavated the enormous Chicxulub crater and launched rock, dust, and vapor into the atmosphere. Dust, soot, and sulfate aerosols reduced sunlight and produced a severe impact winter. Plants and plankton lost sunlight, causing food webs on land and in the ocean to break from the bottom upward. Near and far from the crater, earthquakes, tsunamis, ejecta, and fires added short-term devastation. Around 3/4 of species disappeared, including non-avian dinosaurs, ammonites, and many marine plankton groups. Birds, mammals, and other survivors diversified as ecosystems recovered, eventually producing the modern biosphere. The possible sixth mass extinction. Documented modern extinctions have not yet reached the geological 75% threshold. The warning signs are severe. Deforestation, farming, roads, dams, and urban growth remove or fragment the places species need to survive. Overfishing, hunting, and wildlife trade can remove animals faster than populations reproduce. Introduced species, pesticides, plastics, and nutrient pollution can overwhelm native communities and alter food webs. Rapid warming, ocean acidification, fires, and shifting rainfall now affect habitats across the planet. Long before the final individual disappears, shrinking populations weaken pollination, food webs, and ecosystem resilience. Protected habitats, restoration, sustainable use, pollution control, and climate action can still prevent many losses. Ice, volcanoes, and an asteroid began different crises, but climate, ocean chemistry, and food webs repeatedly carried the damage worldwide. Life can adapt to gradual change, but rapid environmental shifts can outrun migration, evolution, and ecosystem recovery. Mass extinctions open ecological space, but recovery takes millions of years and creates a different biosphere. Subscribe for more deep-time science explained, and comment which prehistoric crisis NOVA should investigate next.